All right. Hello, everyone. Welcome to Lecture 3 of Machine Organization and Programming. Just a couple of announcements as we get started. I apologize for the late release of this lecture. I intended to have it done by 8 a.m., and I'm still working on it. So, been up pretty much all night. All right. A couple of other announcements. I'm planning to release Project 1 this evening or tomorrow morning. Tomorrow's lecture is going to be delayed also, probably until the end of the day. It's not going to come out at 8 a.m. And I think looking at how things have been going for the week, I really need to revise that 8 a.m. release time. I'm going to try and get things released by 11 a.m. I'll put that in the email announcement also. I'm still planning to do videos on how to use the terminal and how to use Vim. Those will be coming soon, hopefully by the end of the day or tomorrow morning at the latest. All right, I'm going to start off today with a quick review of the last two lectures, just some highlights and some places where I made mistakes. Then I'm going to talk about converting Java programs to C, just as some examples. I think this is probably a really great way for you guys to just get into the programming in C mode. And if we can spot differences between something you're familiar with and something that's new and find the similarities also, I think that would be really useful. Then I'm going to talk a little bit more about the memory model for how C addresses memory at a very low level, and particular as it applies to arrays and pointers. So we'll be drawing some arrays in our memory model. All right. One more thing. One last announcement. With Vim, people have commented on the Piazza forum about Vim. Vim is highly customizable. Apparently, some people are the default mode doesn't have line numbers. I'll be going ahead and posting my Vim RC file. That's where all of the settings are, where you put them in. You just put that in your home directory, and then you can then Vim automatically knows where to look for that and can use your settings, and you can customize it however you want. I'm still not very happy with the way my Vim is set up on the lab computers, so I might tweak it a little bit before I release that, so you guys and put some comments in the Vim RC so you guys can see how different settings work, so it's actually useful for you guys. Okay, so next up, quick review of the build process with the corrections. All right, so we're going to start with the source file, sum.c. That goes to the preprocessor. This preprocessor does all of the commands that begin with a pound sign. It's going to generate a sum.i file, or also a preprocessed source file, and the command that we need to add to the compiler is the -e. Just real quick, while I'm thinking about it, the mistake I made was right here on the assembler, the one that creates the relocatable object file. That should have been a -lowercase c, not an uppercase c. The uppercase actually completed the entire process and gave us the sum, but we had renamed it sum.o, so it tricked us. It tricked me. Some of you guys caught it, so thank you very much for getting that straightened out, and I can put that correction in. Okay, so after the preprocessor, that does all of the statements that have a pound sign. And so far we've just seen include. And all that include does is copy the entire contents of a file into the file that it's currently working on. The other one we're going to see today is define. And that's going to create a special compiler variable that will let us use basically like symbolic constants to avoid hard coding things too much. All right. After that goes to the compiler proper. This is actually the really hard stage. In fact, we teach an entire class about the compiler proper. It's called compilers. I think that was one of my favorite classes at UW. I highly recommend it. Anyway, this is creating the assembly code file. Keyword or the compiler option is -s for this one. All right. Then the assembler. This is just going to take that assembly code. This is very, very simple as far as processes go. It looks up every single assembly code line in a table, figures out what the binary equivalent is, and just copies and pastes that binary equivalent right over the assembler as the assembly code. This is creating that relocatable object file. Again, lowercase c. I apologize for that mistake. All right, and then finally this goes to the linker, and this is going to take all of the other functions that are defined somewhere else. If it's in the standard library, C knows where to look for them. I don't have to tell it. If it's something I've written, we'll talk about that in a future lecture when we get to that, when we have an example. But the linker is going to take the source code in binary already passed through the assembler in an object file like the printf.o and bring in that code to create a final executable, the sum. Okay, there it is. There's my review. Some other things. Oh yeah, I went and grabbed the man pages for GCC, sorted through them. This is a big deal. That is not easy to read. And I don't intend you guys to read this on the screen. I'm putting the slides up on the web page so you can download these and read this at your leisure on a real screen. But yeah, the codes that stop the compiler before it finishes are known as pass exit codes. And the -c compiles the source files but does not link. The -s stops after the compilation proper but doesn't do the assembler. So this is the one that gives us the assembly code. And -e will stop right after preprocessing. All right. Yeah, I made two other mistakes. I was choosing the wrong language when I was talking about the warnings. -w all turns on a whole bunch of warnings for things that are generally bad style. Lots of options here, and I really like this. This doesn't actually stop compilation. The one I was referring to was werr. This is the one that turns all warnings into errors and will stop compilation. Or I guess it tries to finish, but it doesn't actually successfully create a file. It just prints out all of these things as errors. This is the one I've been using the words for, and this is the one that I really meant, and the one we have been using. To apologize about that little mix-up. That was me choosing the wrong word. All right. Okay, so next I'm going to move on. I'm going to go to a Java to C translation demo and just talk about how that works. To get started, I've got two files available on the Canvas page for you guys to download. Let me quick switch over to PowerShell. This is what I'm using as my terminal on a Windows machine. It accepts the Linux commands. I've also got the regular CMD or command terminal available, but that uses Windows' own special version of commands, and I want to make this as universal as possible. So in my users Mike desktop Java directory, I've already put the files that I've downloaded from the Canvas page. They're right here, and I was experimenting with a little bit, but we've got helloworld.java and volumeofcylinder.java. So we'll be translating both of these into C code. So what I want to do is actually put them on the lab machines. I want to show you how to do the file transfer so you guys can do this, and then we'll use the lab machines to run all of this stuff. Okay, so I'm going to switch over here to the lab machine. I'm already logged into Royal 30, and I need the working directory so I know where to copy this into. So my home directory is the root udo dosher. So this is already going to be included for me. The only part of this I need is then going to be, I need the private teaching CS354 lecture 03 to put this in the right spot where I'm going to be working. So I'm going to do this from PowerShell. If you're on a Mac or Linux machine already, all you need is the program called Secure Copy, SCP, and then you can just put in the files that you're going to copy. Here I'm just going to do star.java. The star is a wildcard that will get me both Hello World and Volume of Cylinder. So it's going to copy both files at the same time. And then I need dosher.best Linux CS whisk edu. Okay, and after that, this is the computer I'm going to be connected to. The best Linux.cs whisk edu is the computer I'm connecting to. I'm going to be logging in as dosher. And then I need a colon to tell it where I want to put things. So I'm going to go into private, teaching, and these need the forward slashes, CS354, lecture 03. And it is case sensitive. If you put in lowercase, it can't find it. Just make sure you type this exactly right. It took me a couple tries when I was practicing, but I'll get there. All right, if you're on a Windows machine and you have installed PuTTY and that's already working, then we need to do one more change. So the command, just like this, will work on Linux and Mac with no problem. Just secure copy. Now, Windows machines don't come with this secure copy as part of their terminal programs. So I need to go back and add the P here. So this is a different program. It comes with PuTTY. It's PuTTY secure copy. And once I do this, if I haven't made any typos, I made a typo. All right, so what do we do? Oh, I'm an idiot. Okay. I put the at in the wrong spot. You guys are probably laughing at me at home. And that's totally fine. I make mistakes all the time. All right, there we go. So now it's asking me for my password for authentication. Throw that up there, please work. Yep, and it tells me it successfully copied hello world.java and volume of cylinder.java. Okay, so now at this point I'm done with PowerShell. I'm going to just exit out of this. If I go over here in the right directory, I should now see that I've got both of those files present. Looks good. Okay, real quick, I'm going to start with hello world. So first thing I'm going to do is compile hello world. If you've been using Eclipse your whole life, compiling from the command line is incredibly easy. It's just javac, name of the file, and it's going to compile that for me. No error message. It doesn't tell me anything. So in fact, but now I can see I now have the hello world.class file. Now to run this, command is java and hello world. That's all I need. I don't need any extensions on that. And this program just prints out hello world. So let's take a look at the code. All right, so pretty simple. Everything in Java belongs to a class. This one's public. Hello world is the name of my class. All Java programs have a main function inside this class. So, and they've got a bunch of keywords: public, static, void. This is the return type. They require arguments, and then the command to print out hello world is just system out println hello world. Okay, so what I want to do now is take this program and convert it into the equivalent C program and talk about all the little differences between this and C. So the first thing I'm going to do is I'm going to copy hello world into a new file. So the command to do that from the terminal is just cp world. So I'm going to copy this and I'm going to rename it hello world.c. So this will actually take the, let me make sure that worked. Yes, there it is over on the left, hello world.c. So this will take the code and just copy it over directly. Now this is still Java code. First thing I want to do is convert this into C code. All right. First major difference is C does not have classes. It's not an object-oriented programming language. It's procedural programming language. So I'm in command mode. I'm going to get rid of this class line. In Vim, it's just dd will delete a whole line, and I need to get rid of that last curly brace. Okay, next thing we need, main in C actually returns an int and doesn't require any of these other specifiers. It's not going to be public, it's not going to be static. So I'm just going to go back into insert mode, and now I can just push delete and get rid of all of this stuff, and I need to replace that void with a main with an int. Okay, next thing, C actually works the very same way. It takes command line arguments. However, they're optional. If we don't need them, I'm going to take them out just for simplicity, and it's going to save memory and make it go faster. So, and we'll talk about how to do command line arguments in a future lecture. It works a little differently, but we need to talk about arrays and pointers before we do that. Okay, so far so good. And then finally, the command to print something out in C is actually a little bit simpler. We need to actually call a function. It's the printf function. So I just need to remove the rest of those decorators and throw the f on the end of that. And lastly, printf is a function that's found in the standard IO library. So we need to include that. Include stdio.h. Okay, that's the name of the library where that's found. And now C does not care about indentation. It's not like Python. Oh, I forgot one more thing. Timeout. Because main returns an integer, I need to put in that return int to indicate that everything works successfully. So my error code at the end is a 0. Okay. Yeah. So I was saying that C is not like Python. Indentation does not matter at all. However, I'm neurotic and I want it to look good. So I'm going to go ahead and tab everything over so that it's indented and looks nice. In fact, I noticed that some of these are tabs and some of these are spaces. So I'm going to go back and fix my Vim RC before I give it to you guys so that it's automatically going to switch everything to 4 spaces. And I'll show you in the how to use the Vim module that I'm going to put together, how to change that should you want it to look differently. Okay, so at this point I'm going to write this and then quit back to the terminal. And now I should be able to compile this. So GCC, my output file is going to be, I forgot the O. Just hello world. So this is pretty common to use the same name of the file as the source code, which is hello world.c. I want to compile for a 32-bit machine, and I want all the warnings turned on just in case I did something. Yeah, so it's really common to use the same name as the source code, but it's not required. You can name it anything you want. All right, looks like everything worked. I didn't make any mistakes. Otherwise, there would have been an error message or a warning. And now I can just type /hello world, and it's going to print out hello world. Oh, I do see one more difference between C and Java. Let me go back and edit. There it is, my file. So printf in Java, the standard system out print line or print puts a new line character at the end automatically, whereas in C it does not. So one real quick addition, and now it works the same. So up here is my Java version, Java Hello World, and here is my C version. Okay, next let's take a look at that other program. So clear that screen. It's called Volume of Cylinder. So the first thing I'm going to do is compile this, run it, and see what it does. So Java C, Volume of Cylinder. That looks good. Now I have the Java volume of cylinder.class file. Now to run this, Java volume of cylinder, that should work. This is going to ask me for the radius of a cylinder. Let's go with 10. And the height of the cylinder, 10. And it's just going to print out the volume. The volume of the cylinder is 3,141. Pi times radius squared times the height. Yeah, that looks good to me, 3.14159. Okay, next up, let's take a look at the code and see what this is really doing. So vim volume of cylinder.java. Okay, so as we look through this, it's going to need the scanner to take the input that it asks for the height and the radius of the cylinder. So that's going to be the utility we use for that functionality. Again, public class, everything belongs to a class. And then program execution begins with main right here. And again, that requires those decorators, public static, return type is void, and requires arguments. And those are optional in C. And then it looks up pi from the math library and stores that in a constant. So essentially the Java final is equivalent to the C const. For things like numeric constants, things we don't want to change. And in C, things where we stick const on, go faster. Okay, then it creates the scanner object. So this is an object-oriented programming language again. The new is going to mean that it'll be creating that on the heap. And we'll need to delete that at the end when we're done with it. Declare a variable. This works exactly the same in C. Print out that prompt. We'll need to just do a little quick update because printing works almost the same as well. Then this is where we grab the input. This will be different for C. I'll show you in a second. Then the next prompt, get the next value. Variable declaration is going to work the same. Arithmetic works the same. And then we print out the volume. Finally, because we created that scanner on the heap, we'll need to close that. All right, so I'm going to exit this real quick. I'm going to make a copy of this. Copy volume of cylinder.java, and I'm going to rename this volume of cylinder.c. Okay, now I've got an exact copy of the code, and I can just go in and edit it. So vim volume of cylinder.c. Okay, So as we go through this, first, I'm still in command mode, so I can just delete that line right there for the scanner. We will not be using that. It's not a Java program, we'll get rid of that. We don't need a class. C does not have classes, it's on procedural programming. So I'm going to get rid of that last bracket too. Program execution begins here. This documentation string, not valid in C, so I'm going to get rid of 4 lines by typing 4dd. And then I'm going to go to insert mode. So I pushed I to get there. I'm going to get rid of this extra decorators. We don't need those. And main returns an int. Okay, so I'm going to go straight down to the end and make sure that I return. That was kind of loud. Apologize that. Read that message later. Okay, and then int does take arguments for reading things from the command line, but we're not doing that. So I'm just going to get rid of these and leave them out. It makes it run faster. Okay, next up, declare a constant for pi. Okay, that numerical constant for pi in C is actually stored in the math.h, so I'm going to include that library. Include, and I need the angle brackets because this is a library file. Math.h, quotation marks if it's something I've written myself. Those are the only 2 options. Include math.h, and then instead of final, the keyword in C is const for something that I don't want to change. And I'm just going to go ahead and leave this as pi. But the actual numerical constant in math library is m_pi. And I've included that already, so it looks good. All right, we don't need the scanner to grab input, so I'm going to delete that. And then the variable for the radius of a cylinder, this is exactly the same. I'm just going to leave that. We'll be using a double for that. The prompt, minor change here. This just needs to be a printf. Declare the radius, enter the radius of the cylinder. And yep, in C, I'll add a little space there so we don't have to write directly next to the prompt. In C, that printf statement is included in the standard IO library. So I need to include that library so the printf will work. All right, the next thing, this is going to be different. Assign the radius entered by the user to the variable radius. Okay, so I can just use input, my scanner, in Java. However, in C, I need to do something a little different. The function is scanf, and then this takes a format string, just like the printf does. And that format string requires the format specifier for what data type I want to grab. So the format specifier for a double is LF. I believe it stands for long float. So float would be just F. LF is long float, so it's a double precision number. And then I need to give it the variable name that I'm going to be storing this in, radius. However, it's not just the name of the variable. What I really need is the address of that variable. And we'll be coming up and talking about pointers at the end of this lecture. The ampersand is the address of operator, and that's what's required by scanf. Oh, I spelled that wrong too. Scanf. Okay, so that's pretty much how that works. Then the next thing, just real quick, change this print for the other prompt. I'm going to add a space right there. Declare a variable. Yep. In C, we can't do all of this in one line because I need the variable to exist first, and then I need to use the scanf function to fill it in. %LF, because it's double, ampersand to get the address of, and then height. Oh, I forgot my semicolon up here too when I wrote that line. Okay, so then delete the rest of this line. Okay, very good. So now, declare a variable for the volume of the cylinder. Perfect. Variable declaration works pretty much the same. Computation works pretty much the same, so I don't need to make any changes to this arithmetic. And then to print out the final answer, just a printf statement. Java has a printf statement also that does take a format string, and volume of the cylinder is, yep, so this is the format specifier, the %. The F means we'll be printing out a floating point number. And then this actually takes 2 more options, a number of options, but the first thing I can add here is how many spaces wide I'm going to reserve for this number. So if I were to put something there, it's going to reserve 6 boxes, 6 characters. I'm not going to do that. I'm just going to use however many I need. So I'm going to leave that out. And then period 2, period 2 is going to tell me the precision with which I want to print out the answer. So in this case, I want it to 2 decimal places, and then throw a new line on the end of that. Finally, at the end, there is no scanner, so I'm going to get rid of those things, and I need to return 0. All right, so I'm going to go compile this and figure out all the mistakes I made. So write, quit, and then GCC. The output file is going to be volume of cylinder. Got a typo here. -O, not a 0, leave space. Okay, input file, volume of cylinder.c. Everything we'll do will be for 32-bit machines, and I want to know everything I messed up, so I'm going to throw in the print out all day warnings. Oh, first try, no mistakes. All right, let me just make sure that it is actually here. Yep, there it is, volume of cylinder in green with the star, meaning it's executable. I spelled it wrong. Oh, volume of cylinder. I'll fix that later. And then when I run this, enter the radius of the cylinder, we'll do 10 again. Enter the height of the cylinder, 10 again, and it should give us the same answer. 3.14159 times 10 times 10 times 10. So that looks good to me. One more thing I want to highlight that I forgot to mention when I was talking about arithmetic. Let me go back and take a look at this. So if we wanted to do the volume of a cone, I'm right here. I'm going to declare a variable to restore that. The formula for the volume of a cone is very similar. It's just 1/3 of the volume of the cylinder. Perfect. Now I can print this out. Printf. I'm going to just go to command mode, copy and paste that line. And then just a little bit of editing. The volume of the cone is, and then I need to change my variable here. I called it something different. Volume of cone. Okay. Now, you guys at home, if you spotted the mistake already, the error, you're probably screaming at me. But look very carefully at the last few lines that I just wrote. There is an error here. This code will run. It'll definitely compile. It's a semantic error. See if you can spot it. Okay, I'm going to actually just go run this, show you what the results display. So, right, quit, compile. Let's get the right name in here this time. Volume of cylinder. And now when I run this, volume of cylinder, 10, 10 for the radius and height. And now it's not actually printing out 1/3 of 1,141. That would be about 1,000. It's instead giving me 0. Let's go take a look at that code real quick one more time. The answer is that this is actually doing integer division. So it's taking 1, divides by 3. So 1 doesn't go into 3, or 3 doesn't go into 1 at all, so that the division gives me 0 with a remainder of 1. So what I really need to do is change these numbers to floating point numbers in order to get that 0.333 to make this work. I've got several ways I can do that. I can actually go ahead and add the .0 to either one of these operands. I only need to do one. So the division operator takes two things. It takes two arguments, one on each side of it. And if either of them is a float, then it does floating point division. If they're both integers, then it does integer division. So that's one way to do it. Another way would be to cast one of these variables to a float, and then it's going to use floating point numbers, or a double. Spell it right, Mike. So, and to cast a number to a double, all we need to do is stick the prefix double in parentheses around it. And this is how typecasting is done. So that's a second way to do it. And we only need to do one of them. As soon as one of these is a double or a float, then it will take care of doing all the rest of the type conversion for me. Finally, another option would be to just take the volume, which is already a float, and divide by 3. This will save me some math operations, some type conversion. This is probably the fastest way to do it. So I'm going to leave it like this. I'm going to quit and go back and just make sure that I actually successfully completed that correction. There we go. Yep, volume of cone 1047. That's about a third of this, so that looks good to me. Next, I want to give you guys a little bit of background into the development of C. C was developed by Dennis Ritchie and Ken Thompson in 1972 at Bell Laboratories. These guys were working on the Unix operating system. They were developing this at the time. And back then, in 1972, operating systems were all written in assembly. And this just got to the point where it was too complicated. It was too difficult to actually write what they wanted for a decent operating system in assembly. So they needed a higher level programming language. The problem was higher level programming languages at the time just didn't have the power to develop efficient enough assembly code from the high level language code. So these guys dove into this problem and developed C out of this. They were working on a PDP-11, and in 1972 this was a 16-bit machine with 128 kilobytes of main memory. So my computer here on my desktop is a 64-bit machine and has 16 gigabytes of memory, so substantially more. And in fact, running the compiler actually took a quarter of the main memory just to run the compiler, 32 kilobytes. All right, this is where the CPU would be down at the bottom of this device, and 20 users would connect to this simultaneously using dumb terminals. Dumb meaning they didn't have their own CPU. The connection speed, I looked this up. I think I made a guess last time, but the connection speed was actually about 10 characters per second, and the C compiler could compile about 3 lines per second. That means the volume of the cylinder program that we just wrote, it had just over 1,000 characters and 40 lines. It would take approximately 2 minutes to send all of this data to the CPU and compile the code. So the design philosophy behind the development of C focuses on efficiency and speed. Some of the things you guys are going to observe and almost certainly run into trouble with, I do all the time still, there are absolutely no safety checks. It doesn't check to see if you've been assigned a variable. It'll reserve space for it, and you can just use whatever garbage is in memory when it gives you the location. But it doesn't check to see that you actually assigned it a value. It doesn't check to see that you're using array indices that are actually in bounds. You're responsible for your own memory management and garbage collection. None of that is done automatically. That would take valuable resources that, in the hands of an expert programmer, they can take care of it. And it's also very space efficient. To store a 16-character string requires 17 bytes of data. In Java, that same string takes 76 bytes. So the language was written with a number of features that allow the programmer essentially direct access to the memory. You can even make recommendations about which register that you want the CPU to use for certain computations, because you might be able to make it go even a little faster. So this language was developed for systems programming, for developing operating systems and for developing code that will interact with other devices on your computer, like your graphics card or something like that. Next, I'd like to talk a little bit more about the memory model in a computer. So here I've drawn a bunch of memory slots. Each of these are 1 byte, so they'll hold 1 character. I've got the memory addresses over here on the left. 1 second, let me grab my row pointer. So there, now it will display on me. So each of these represents the memory address. The memory addresses are labeled in hexadecimal because it's actually, they're accessed by a bit pattern. And so it just makes sense to do that for memory. So each of these are 1 byte. They'll hold 1 character. It takes 4 of them to hold an integer. And this particular memory model has 32 if you count them. So I've got them numbered from 00 to 1F. And just so this is clear, there was some confusion about like a 32-bit machine versus a 64-bit machine. We're going to compile all of our code for 32-bit machines. The number is a little smaller. We don't have to worry about some of the extra complexity. And we still get all of the conceptual understanding behind how things work. And extending to 64 bits is just not that, one more level of complexity that doesn't add much to the course. So 32-bit addresses require, I'm going to take the log of that, the log to 5 bits to describe them. So that means that this machine right here with 32 memory addresses is a 5-bit machine. The minimum address, 00000, would be this top one up here. And the maximum address I can have is where they're all ones, 11111. And that's 1F down over here in the lower right. So, oh yeah, I want to do a little bit about converting from binary to hexadecimal real quick. The easiest way to do this is to break it into chunks. Start on the rightmost side, the 1, 1, 1, 1, those 4 rightmost ones. That's going to give us the rightmost hexadecimal character. And then we'll just take the next chunk of 4. This only happens to have one thing, so we're going to stick 3 zeros in there to get 4 bits that we can turn into another hexadecimal digit. In this case, this translates to 1. So that maximum address there, 1F. Okay, in a second, we're going to start talking about arrays in C. So just as a quick example, I've got an integer array. Sorry about that. I've got an integer array with 4 items in it, 10, 20, 30, and 40. So I'm just going to put this into memory. I'm going to switch back over to editing mode so I can just do this live. So the first thing, when we remember how bit patterns work, the first element there, the rightmost one, is the least significant. It's going to represent a 1. Then the second bit from the right is going to be 2. Third bit from the right will be 4. The fourth bit from the right will be 8, and then 16, and then 32. So when I write these numbers in, so if I'm taking the number 10 in decimal and I want to convert this to a bit pattern, I'm just going to ask myself, can I divide it by 32? The answer is no. Can I divide it by 16? No. Can I divide it by 8? Yes. So I need a 1 for that. When I do that, I get a remainder of 2. So now, can I take 2 and divide it by 4? No. Can I take, so that'll give me a 0. Can I take 2 and divide it by 2? The answer is yes. That gives me a range of 0. And then for the rest of these, I'm just going to put in, whoops. Oh dear. Having trouble typing today. A 0 for that 1, because 0 divided by 1 doesn't happen. Okay, so I'm just going to do a couple more of these, just as a quick example. All right, so 20. I'm going to say, or maybe I should put in the rest of these digits too, because I've got 6 bits here. So I'll just keep 6 bits here. So can 20 be divided by 32? No, so that's going to be a 0. Can 20 be divided by 16? Yes. The remainder is 4. Can 4 be divided by 8? No. Can 4 be divided by 4? Yes. Remainder is 0. So once I get to remainder 0, I need to put in a 0 for the 2 and a 0 for the 1. So that'll be 20 in binary. All right, then 30. Same thing again. Can 30 be divided by 32? No. What about 16? Yes. So 30 divided by 16 is a remainder of 14. So it can be divided by 8. Let's see, 14 subtract 8 is 6. That can be divided by 4 and 2, but not 1. All right, did I do that right? Let me see here. 16 plus 8 is 24, plus 4 is 28, plus 2 is 30. That looks good to me. One last one. You guys pause the video, try and do this on your own, and then we'll check the answer together. Okay, unpause the video, and here we go. Can 40 be divided by 32? Yes. So we'll put a 1 there. That's going to give me a remainder of 8. So cannot be divided by 16. Can be divided by 8. The remainder is now 0, so the rest of these, the 4, 2, and 1, will all give me zeros. Okay, excellent. Now, next thing I'd like to remember is that integers, when they're stored in C, are actually 4 bytes. So if I start putting an integer into this very first memory slot, like the 10 here, 10 is actually going to be not just this number, but we'll have 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 1, 0, 1, 0. All right, let me shrink that so it actually looks good. Is that enough? Okay, so this is the actual bit pattern that's going to be stored in memory. So I'm just going to go ahead and put this in right now. Okay, so I've got the very first integer in my array, the 10, stuck into memory. It takes up 4 slots. When I talk about the location in memory, I'm always going to refer to the very first position, even if it's a multi-byte data element. So in this case, the memory location of the first element of this array, the 10, is actually going to be memory location 0, 0. So Yeah, real quick. I'm going to pause the video and put a little note in. Okay, I've made a little note here that array element 0, so this is how you index into an array in C, just like Java, is pointing to this memory location. It takes up 4 bytes. So all of this in the red box is a member of element 0 of this array. So I keep going. If I want to put in the next element, so this would be the 20, and then let's see, that's 0, 0, 0, 1, 0, 1, 0, 0. Okay, so this is now going to be element 2. Whoops, copy Mike. Make a copy. Grab copy the arrow. And this element is going to be starting at byte number 4. There we go, that looks good to me. And let me just draw another box, grab a box around this. So this is also going to take up 4 bytes. So the first position is at element 0, the second position is at element 4, or memory location 4. I'm going to pause the recording, I'm going to put the rest of these in and just fill up the entire memory model with... Okay, I've filled in the rest of this. I'm about to jump over and actually create this same array in C code, and we'll use some of these new operators we've learned about the address of, and I'm going to introduce pointers to talk about what it really looks like in code. But this, I just want you guys to have this picture in the back of your mind. I want you to recognize that even though these numbers, like 10, only actually takes up 4 bits of information, it still requires all 32, and most of those bits are just 0. So, and the other thing I want to highlight is the positions. So array element 0 is at 0, 0. Element 1 is not at 0, 1. It's actually byte number 4 where this starts out, and then byte number 8, and then byte number C. All right, let me go pop back over to the terminal, and we'll go through some of this live. Let me just make a real quick new file. Let me switch to the correct screen. So let me make sure, yeah, looks like I'm recording the terminal, good. So Vim, let's call this arrays and pointers.c. Okay, when I pull this up, I'm just going to write a little bit of code. So first up, int main, don't need any parameters from the command line, return 0, and I'm going to be printing out a bunch of stuff, so I will need to include standard io.h. Okay, first thing I want to do is just declare an array and go through just like we've been talking about. To declare an array in C, all I need to do is give it the name, and I'm going to call this ARR. I need some brackets here, and then I can put in the elements of my arrays, 10, 20, 30, 40. And now what I really would be good is to put in the number of elements inside those brackets. If C can determine from the array by just counting how many elements are, I can leave that out and it'll default initialize to the correct number. I'm going to try and be as specific as possible as I do things. So I'm going to need a semicolon at the end of that line. So this is enough to declare an array. To access elements of the array, suppose I want to change an element. I can say array element 0 equals 15, and that will change it from 10 to 15. So array access just with brackets, exactly the same as in Java. So let's print out some of these. In fact, I'd like to print out all of them. So I'm going to use a loop for this. For int I equals 0, I less than 4, I plus plus. I pretty much always use brackets, even when they're not required. This just gives me the scope for this for loop and lets me put in more than one statement. So, but I'm going to be printing these out. So I of, and then here I want a decimal. Oh, and I really need ARR equals, and then I'm going to put in the actual value of that, and we'll throw a new line on the end. So then I've got 2 format specifiers. The first one I'm going to be putting in is the index of my array, and the other one is the actual value of the array. So that's array I. All right, let me just take a look and see what this looks like. GCC, output file, arrays and pointers. Oh, if I were to compile it like this would take all of the code that I just wrote. It would compile it, it'd generate binary, and it would save it in a file, arraysandpointers.c, with the exact same name. And that would nuke the program I just wrote, and I'd have to type it all again. Don't worry, if I ever do that, I'll do it off camera. All right, and then, so I would need to make sure I delete that. M32 and all the warnings. All right, let's find out all the typos I made. Did that really work on the first try? Do I have arrays and pointers? Let's try this out. So I'm going to just run arrays and pointers, and it's printing out everything. So array 0, I changed that to 15. Array element 1 is a 20, 2 is 30, 3 is 40. Okay, that looks good so far. Okay, the next thing I want to do is talk about where these are actually stored in memory and how we can get that information out of C. So let me go back to my, right window, editing, and I'm going to add one more thing. So if I want to grab the address of something, the command that I need is, so let me just put it in there. We'll just print it out. So I've got array element I is equal to the value, and then I'm just going to put at address, and then we'll put in a %d right here. And I need one more thing. What I really want is the address of operator. I talked about this a little bit ago at the beginning of class. Array element I. So this is going to look up where it's located. I'm going to write quit and then go find out which typo I made. Okay, it did give me something. Oh, I've got all warnings turned on. It says that format D is for decimal arguments and expects type of integer. But the argument I'm actually is a pointer to an integer or an address. So it tells me that what I really want is something different. So let me go back and edit this. They're absolutely correct. The format specifier for an address is actually %p. All right, so let's try this again. Yep, no warnings this time. So let's run this. And now, here's what we're looking at. Array element 0 is still 15, and now we can see that it's located at address. So this much is hexadecimal, FFDCD05C. So this is the starting address. And now check this out. 4 bytes later, so we've got C, and D, E, and F. So C, D, E, and F are all going to be included with that one element of the array. It takes 4 bytes to store that integer. Then next we can see the next element is at 60. And then after that, 64 and 68. Oh, one other thing I'd like to show you guys is how do I actually grab the size of something if I don't know it. So let me just put this right up at the top. And I'm going to just print out the size of something. Printf, size of int is %d, new line, close the format string. And then to get the size of something, the command is actually just size of. So that should be enough to do that. That should close the printf and semicolon. And we can see that the size of an int is 4. And this is going to be a number that's given to us in bytes. So we can do this for pretty much everything. In fact, I'm curious. So we have a couple of other types too of integers. We've got those specifiers. Decorators, I forget what I called them last time. We have short and long. The only thing the language specifies about short and long is that short needs to be at least 2 bytes and less than or equal to the size of an integer. And long needs to be greater than or equal to the size of an integer. And what do we have? So size of an integer is 4. Size of short is 2, and size of long is 4. Okay, so on the exams, I will always tell you how big things are. You can always assume that an integer is size 4, however, that's very standard. But for short and long, I'll tell you how big they are, how many bytes they consume. So next up, I'd like to introduce the idea of pointers. So a pointer is a variable that holds a memory address of a variable. Okay, that's all there is to it. You think, okay, that's very simple. But to be honest, I never got pointers the first time I took a class like this. It took me a long time to figure this out. pointers are extremely powerful and allow you to write very efficient code to do things. So it's worth spending the time. If you haven't figured them out in another class, this is the one. Make sure you get this now. We're going to use it a lot for low-level memory access. So let me just give you an example. If I have a variable, integers holding an integer n with the value 3 assigned to it, I can create a pointer to n. I'm just going to call it pn. And I need to give it an address. So I'm going to use the address of operator and give it the address of n. Okay, so let me walk through this. The first thing I'm doing, I'm declaring a variable n. I need to tell it it's of type integer, and I'm giving it a value. The star here is the symbol. We're going to use the star in two ways today. It's actually two operators that use the same symbol. This first one is a pointer declaration. And a pointer declaration is something that looks like a type followed by a star. So I've got int star, char star, float star, double star, and we'll have more later. But for right now, it's always a type followed by a star. Okay, and I can put this any one of three places. I can write int star pn, or I can write int star pn, or I can write int space star pn. So I've got all these options. And when you're looking at code review, let me throw some semicolons in. When you're doing code review for the company you work for someday, people are going to argue endlessly about where the star goes. Personally, I always go with this third option. And the reason I do that is because I can declare more than one pointer on the same line. In fact, I can declare a variable x, and I can have a pointer px, and I can have another variable y, and I can have a pointer to y, py. There we go. I can declare all of this stuff on the same line. So this is just a regular variable. It's going to hold a value. This is going to be a pointer to something. Later on, I will assign it to x, and I can do that like this. Px is equal to the address of x, and py is equal to the address of y. Even though I haven't assigned them values yet, I can do all this stuff. So this is the reason I put the star next to the pointer rather than putting it in the middle with a space or next to the integer. That just makes it confusing if I have more than one thing that I'm declaring on the same line. And so I can let me just demo a couple of things real quick. So I can say that x is equal to 3, and then I can print out x equals, we'll get a format specifier, and px equals, because it points to the exact same memory location. So I'm going to introduce some, let me just do it this way. Px is the memory location of x, so this is going to be %. It's a memory, so the format specifier there is %p. And I'm going to do one more thing on the same line because this is just going to be a memory address. To follow a memory address, to go get the data at something, I need the dereference operator. So that's just going to be star px. So this star is different from the star here. This star follows a type. This one does not follow a type. So that means px must be a pointer. Follow that memory address to wherever it goes. So let me finish this line. Px equals %d. So this will be a value because I'm going to chase it down. And then I've got x, px, and star px. Okay, let me run this and show you guys what I'm really meaning. All right, quit. Oh, I forgot the new line. Okay, so x is equal to 3. I assigned it a value. Px is the pointer. This holds a memory address, so it's in hexadecimal. Check it out. This was at 08. Then we've declared some variables. This one is much further down. Well, not that much. Oh, it's actually ahead of this. Yeah, it's up here in memory, before the array. Yep. C is going to control where it sticks things. Px, when I do the dereferencing, this says follow that and chase it down to a 3. All right, I'm going to hop back over to PowerPoint with my memory model and kind of explain what's going on here. All right, I've got some more PowerPoint slides built. Just want to go through that demo I just did in code and demo this with a real picture of memory. So hopefully this will be clear. So I'm declaring a variable x and storing a number 3 in it. And C gets to decide exactly where it's going to put that variable. I picked this spot over here for my model. And again, it's going to take up 4 bytes. And the number 3 is 1, 1 in binary. And the rest of these are just going to be all zeros. So this is where it's stored in position 1C. When I print it out, I get 3 exactly like I'd expect. Then, if I go back and add some more stuff to my code, if I add a pointer and give that the address of x, so C again is going to choose a location in memory to store this. All right, so I picked right here at position 18. Again, pointers are 4 bytes long in a 32-bit machine. So I'm going to go ahead and just pretend this is 32 bits now. And the address or the value that it's going to store here is the address of x. And it's going to be the first byte that it's used. So this is going to store 1C. So if I look here, 1C in binary, if I take the last 4 bits here, 1100 is C. The equivalent of, let's see, 8 plus 4, 12. And then the 1 here is the first 4 bits of the last byte. So this is the least significant byte. Is that just 001? Because I just prepend 3 zeros. Okay, so that's what's stored in this position right here. So the address where this is stored is 18. That's not important. We don't care about that. The value here stored is an address, and it happens to be the address for x. So when I print this out, it's printing out the address of x. And then if I do one more thing, if I go ahead and use the dereferencing, the idea here is that it says don't print out the address that's actually, don't print out the value that's actually here. What's here is an address. Follow that, take this address and go look up whatever is there and print that out instead. So in this case, it is a decimal value because x is an integer. And so when we dereference it, it follows this arrow and prints out this number, which is, when we translate the binary into decimal, is going to be 3. All right, I'm back over here in Vim. I just want to highlight one more thing in that I can also use pointers to access the same location. So I can take star py. Please remember here in line 22, I'm saying that py points to the address of y. So when I dereference that, I can say py is equal to 5. And now both x and y, or py, dereference py, have the same value. So let me just grab a copy of this print line. We'll paste that in here. And now let's print out y. We'll do py. Whoops, I missed. Py. Dereference py. Y. Raise and point. Compile. Still giving me a warning for an unused pointer. I haven't done anything with that one yet. So when you run this, now I can see that y is given the value 5, even though I didn't directly assign y. I used the pointer dereference to give it a value. Py over here has a different memory address. It's actually right next to the other pointer in memory, just 4 bytes greater. And yet still E618. Yep, still in front of the array here. Okay, and then py dereferenced, when I trace that down, does give me the 5. All right, so the next thing I want to talk about is pointers and arrays and how they're connected. So if I have an array of integers, if I'm on the right screen and have an array of integers, so we'll just make int, we'll call this array A, and we'll give it some values. 1, 2, 3, 4, 5. We're computer scientists. We'll start with 0. 1, 2, 3, 4, 5, 0. All right, there we go. And then technically an array is a pointer. But it's constant. All right, let me demo that. So if I declare a pointer to an integer, and we'll call that just straight up p right now. I don't think I've used p directly. I can say that p is equal to a. So a is going to be an array in memory. Each of these takes up 4 bytes. This might be at location 0. This might be at location 4. This will be at 8. The pointer is going to be somewhere else. This might be at location, IC or something like 1C, something like that. And then because it's a pointer, I can directly give it the address of A. And I don't need the address operator because arrays are already pointers. So I can assign one pointer to another just like I can an integer to an integer variable. Okay. So let me next print some of this stuff out just so we can see what's going on the inside. So I can take a of 0 and print this out equals, that'll be an integer value. And then I can do the exact same thing with my pointer. So pointer is also, array is a pointer is a pointer. I can access them the same way. So p of 0 will give me the first element of that array. So p0 equals %d, new line, quote, and then I've got two things here. I've got a of 0 and p of 0 that I want to print out. So let me just show you this works. They should print out two zeros. Let's throw some space in between them. We'll give them a tab. Right, quit, compile, and run this. So A0 is 0, P0 is the exact same thing. It's also 0. Let's edit this. I could go ahead, make another copy of this. Let's do element 1, just in case you think everything may have been default initialized to 0. In general, C does not default initialize anything. That's part of that speed and efficiency. So run this again. So element 1 was 1 and P1 also 1. It's the exact same memory location that we're reading. Now, one of the cool things we can do with pointers is I can go back. I'm just going to insert mode tab. Okay, here we go. Print out I'm going to dereference P. We'll print this out first. So dereference P. This should be a 0. And then I'm going to print, here's what I want to do. I'm going to take P equals P plus 1. I'm going to increment it. So give you the answer right now. C actually knows how big this is, and it's going to actually increment it by 4 and not 1 to move it down by 4 bytes. So let me do one more thing. So I've got P printed out equals, I forgot the %d. Move this over just to show you guys that it does actually increment it. I'm also going to print out as regular P is equal to format specifier P. Okay, yep, so I'm printing out the address, and that's the address in pointer notation, and I'm printing out the value. So the first time I do this, it should be 0 and some address. Then I'm going to increment P, P plus equals P plus 1. I'm going to print this out again. And then, just to show you guys that this works too, P plus plus, copy and paste that line yet again. And maybe one more time. We'll do P plus equals 1, just to show that, show off all the different options for incrementing. And then we'll paste that line there one more time. Save this. Compile. Oh, it looks like I made a mistake somewhere. Did I mean printf? Yes, I did. So where did I forget it? Oh, all over the place. Printf. Printf. Okay, so check this out. Now, when I first started out, P is pointed to the same location as the array, A0. So it prints out a 0. And here's the address of that. And yeah, I created a new array. So this is the first time we're actually seeing this particular address. And then I incremented the pointer P. And check it out, the address actually incremented by 4, not 1. And that's because C knows that the size of an integer is 4 bytes. So it automatically took care of that, and I didn't need to remember how many bytes are in an integer. Then I used the other two techniques. This was I++ and I plus equals 1, still incrementing by the correct amount, and showing me the next couple of values of the array. All right, I'm going to do this in a loop real quick. So go back to edit this. First up, I believe I have a new line. And copy and paste my new line down here. So I'm just going to go for, in this case, I've already got a pointer declared. So I'm just going to leave this blank. I'm just going to use that same pointer. Oh wait, I've already incremented it. Here, let me do this. I'm going to create a new pointer to an integer. I believe I have one available, pn. I think I already had a pn. Pn is going to be equal to the array. Hold on, let me double check that. There it is right there. No, right here. I need this. So now I have a pn pointer. I'm going to point that to the array, and while pn is not equal to, how many elements were in the array? Were there 4? 0, sure. 0, 1, 2, 3, 4. Well, it's not equal to that last to that element. I'm going to increment the pointer, and then we'll just print this out. How about copy this line, and this is not p, it's now pn, 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 pn. Warning, comparison between pointer and integer. Oh, I do need the address if I'm... So in this case, I'm not, here I'm using array. Array by itself is a pointer. Array where I've used the index is an actual location, or the actual value. So I need to go ahead and use the address of array of 4. Now I'll be stopping at the right point. So compile. Did we get any warnings? Error. N is undeclared. That was up here. So I commented this out, so I stopped getting the warning. And then I only put back one of these. So there we go. Let's do this. Just put those back. Now we'll get a warning that I'm not using N. Ooh, it didn't give me a warning. I must be using it. Okay, so now I compiled this. Should be able to run this. Yep, here we go. So the first thing that we see... Oh, did I set it to point it to the first array? Okay, excellent. Now I can see these addresses are the same. I was thinking I was using array A, but I've got array ARR. Okay, focus mic. So here what we've got is the pointer dereferenced is pointing to that very first element of array. So ARR0 is 15. And here's the address of that. And then my loop is going to increment pointer for me automatically. So now it's pointing to this address right there and grabbing the value 20 from this array up here. And then it's doing the same thing until we reach that stopping condition where the pointer is actually equal to the address of the final element. And that's when it's going to stop. One final thing that I want to demonstrate. So this array, let me go up to the top right here, has elements 0, 1, 2, and 3. So this actually would have been one element past the end of the array. And sure, it's just going to keep incrementing the pointer as many times as it needs to. Whoops. Hold on, grab the wrong spot. And there's no checks on array bounds. I can, in fact, let me just grab this line right here. Yeah, I'll do it this way. I'm going to go ahead and say, let's take P is equal to A. So now it's pointing to the very start of this array. This array has 0, 1, 2, 3, 4, 5 elements in it. So what I'm going to do next is say P is actually equal to P plus 25. So that should increment this by 100 bytes, and we're looking at some memory out in the middle of nowhere. one more detail. I want to print out where it starts and make sure that I am really getting 0. Then we'll increment it, we'll print it out and make sure we're getting an address that's much bigger. And this should not generate a warning. C doesn't bother to check. No warning, no error. It does not care that I'm accessing data way out in the middle of nowhere. And in fact, here it is. This line here, P0, was the very first element of this array. At this address, there it is, it's the same address right there. So it's at the right spot. And then the next line down, I've got this garbage value because C does not initialize anything. This is out in the middle of nowhere memory. And at this address, which is 100 bytes larger than this one. So 01E4, 02 E. I don't know if that's 100, but it should be 100. Hexadecimal math is hard. Okay, yeah. So C will let us access pretty much any memory. But just a quick note, the operating system has only certain memory addresses that are reserved for this entire program. If we try and access something outside of that memory block where things have been allocated, it's going to crash the program on us. So we're only allowed to use certain memory addresses that the operating system has granted us. Another issue is that those memory addresses hold the instructions for my code, the data for my code like global variables, the heap where I've dynamically allocated memory, and the stack, which is anything that I've declared in a function or in main. All of that memory is reserved. So it's possible that I can overwrite instructions. It's possible that I can overwrite data unintentionally if I'm using array elements that are out of bounds. And in fact, that's how Stack Overflow errors, buffer overflow attacks. And if you take computer security, one of the very first projects will be to write a buffer overflow attack. Let me see. I'm checking my notes. Yep, that's all I want to do for today. Have a great day, guys, and I will see you guys tomorrow.